Hi everyone, thanks for coming along to PyCon. Today I'm just going to discuss a project that I've been working on and off. It's a collaborative GIS project between myself and a group out of the ANU called the Fenner School of Environment and Society. So, as it's probably been mentioned before, I'm actually a scientific specialist programmer working out of the NCI. The NCI actually stands for National Computational Infrastructure. It was formerly known as the ANU Supercomputer Facility, or some people might know it as APAC. We're actually the host of Rygen, which is currently the largest supercomputer in the Southern Hemisphere. Here's a shot of the machine room. It's actually incidentally useful as a film set too. That happened to go recently. So apparently if you see something called the code coming on TV, you'll see it there. We actually provide petabyte storage facilities, and there's also cloud services there too. And we typically host for this ANU Research, CSIRO, Geoscience Australia, and Bureau of Meteorology. So in my day job, I'm developing a lot of GIS sort of software, and I actually support a number of sort of science people there. And this is sort of a rough example here of bridging the gap between scientists and technology. So there was a classification that we were doing, and we have actually sort of draped that over a digital elevation model there. So that's actually Southeast Australia. I don't know how well it's coming up on the screen. My predominant use of Python is for things like basically geospatial processing. There's terrain analysis fits into that as well, prototyping, bits of data analysis, and I also do a bit of sort of data exploration and actually use it quite a bit for testing. So since 2007, I actually collaborated with a group out of the Fenner School at the ANU, so this is their building. They're actually concentrating on environmental problems like sort of the water crisis, climate change, fires, droughts, biodiversity losses is sort of a thing I'm helping them to focus on as well. So the particular research interests of this group are things like modelling flora and fauna response to climate change and atmospheric CO2. And they typically tend to work at like large scale and actually up to the continental scale, because they're trying to treat an ecosystem as a continuous whole. So it means just sort of like working with like all of Australia in a data set at once. And mostly they're geographers. They've got no formal software training, and they're typically just using things like Windows desktop GIS like ArcMap. They'll do a bit of R coding every now and then, and they're sort of stuck on Windows boxes, and they don't have any admin rights. So back in early 2012, they actually contacted me and said, "Oh, help, we need some updated vegetation data." And previously, one of their senior researchers had she'd done all the work to actually produce a number of layers, and it turns out this researcher had already retired. Come on in, Jay. So they sort of left with this, what do we do? No one else could actually repeat this work. It took ages to produce, and they basically gave me a time frame of a couple of months, because apparently some of their CSIRO research partners needed this data fairly soon, and I heard, I don't know if it's true, but it was apparently going to make it into some IPCC reports. So they're sort of interesting. Their idea was they wanted to extract functional leaf type data from digital vegetation information, and there was NASA has got this Terra satellite with these series of instruments called MODIS instruments, that stands for Moderate Resolution Imaging Spectroradiometer. And this actually is a satellite. It just goes and images the Earth sort of every 1 to 2 days, and they wanted to sort of take a subset of that imagery, or something, because there's about 36 instruments on board, and they wanted to actually just use one of the results from one of those. They actually want to sort of take some of this base vegetation data, break that down into 3 different vegetation classes. They called it some turgor, mesic, and sclerophyll. So this encompasses everything from things like grasslands, shrubby woodlands, sort of open forest, closed forest, and rainforest. And the goal is to sort of get these rough vegetation classes for all of Australia over the time series that this MODIS satellite's been taking sort of informational readings. So with that way, they can basically get an idea of vegetation changes across Australia for the past now it's up to about 14 years of data. So this will obviously help with things like if you've got a bushfire, that might actually just completely blitz an area, and then you'll note that, say, the vegetation there will be completely changed, and you can actually sort of track recovery, and or if the types of vegetation might completely change. There's probably the best example I can think of that is if anyone's familiar with the bushfires in Canberra in about 2003, and Mount Stromlo was there. That was actually a pine forested hill, and that actually got completely blitzed in the fires, and it actually became sort of more of a sort of grassland and sort of open shrubby woodland, and it's now actually slowly starting to recover. And the Fenner group, they're looking at mainly using this thing called the MODIS 13Q1 product, or NDVI. NDVI stands for Normalized Difference Vegetation Index, and this is, roughly speaking, it's like a measurement of live green vegetation. So if you've got lower values represent sort of dry vegetation or possibly even bare soil, and higher values, as you get sort of higher up the scale, it's sort of the more green your vegetation, you sort of top out at rainforests. And you end up with multiple acquisitions per year, so you can actually get this, like there's a time series of all this information, so you can actually start to measure change. Unfortunately, we had a copy of this data hosted at NCI. And here's a rough example that I ripped from a NASA site. You can basically see here you've got this brown sort of representing like below average moisture, so it's probably in the middle of a drought. So you can actually see up in the sort of Kosciuszko National Park and Victorian Highlands, you're sort of getting some fairly dry areas. But then if you skip forward 2 years or so, it's actually picked up, and it's been a lot more rainfall perhaps than normal, and it's actually greened up again. So I'll just go into a bit of the actual technical detail of some of the data. You end up with a number of sort of like raster or bitmap images of this data, and it comes in at sort of a 9-second or 250 metre cell. Each data set's about 19,000 by 14,000 cells, so you end up with about 285,000 cells per image. And that's all 16-bit integer data, and you end up with about half a gigabyte a year. Half a gigabyte per image. And there's 23 rasters per year, so you end up, you're basically ending up with about 12 gigabytes a year of data. And this starts in early 2000 and continues to a couple of months before the present day, because there's actually a sort of a processing lag where the CSIRO actually has to sort of do some sort of processing steps to it. And so obviously new acquisitions are adding about 2 layers or a gigabyte per month, basically. It's not huge in high performance computing terms, but it's problematic for like scientists that don't have a technical background. And obviously you can break this NDVI layer down into a number of these functional leaf types that I was talking about earlier. And my particular role was I was given a Word document which said, here's a couple of algorithms, listed a couple of processing steps. There's a bit more detail included in a couple of academic papers that were handed over, and so I started digging through that. Switch slides, that'd help. And it also turned out, there was the existing work that this other scientist had done, so I started to pick through that and find out what was going on with that. So there's basically this data archive that I found that was there was just this, basically looked like someone had gotten their hard drive, dumped it into the archive and left it there. So there was a lot of intermediate files, there was just junk. A lot of this stuff was unknown, it was completely undocumented. I found a couple of Word documents. They didn't actually include any documentation whatsoever. So it was kind of like, oh, hang on, what's actually happening here? I found a couple of data sets, but they're in this weird Addressee raster format, which I'd never heard of before, and it didn't actually contain any metadata, so I couldn't actually track back on history of any of this stuff either. So I was sort of finding out a few more details. It turns out people had, the previous researcher had used this tool called Addressee, and that was this Windows desktop type thing. It was some GIS product that had been started back in about 1987, I think. It made its own additional custom raster format. Fortunately, the GDAL libraries handled that, so I was actually able to read some of the data, and I actually sort of found out more about how sorry? Did someone call out? It turns out that the tool can actually run a bit of has this like a feature to sort of run this thing called macro code, and that actually made a bit more sense because I found one of these strange Word documents contained it was about 20 pages, and it was just lines after lines of what looked like someone had mashed the keyboard. It was sort of full of all these asterisks and odd magic numbers. It was quite obscure, and I actually went trying to find some public documentation on the internet. There was none of it. Basically because it's a proprietary piece of software, no one wanted to actually just release that documentation, so I actually had to get someone to probably illegally send me some PDF pages so I could understand what this thing was. It turns out that think I've lost a slide here. Oh, no, sorry, here we go. Yeah, this is actually an example of one of the lines of code. You've got, as you can see, there's like these magic numbers. They actually turn out to be function arguments. So you've got things like this 1 here might actually mean subtract. If it's a 2, it might mean add. So you're sort of forced to use magic numbers as like a lookup. So you've got to go and buggerize around in this documentation to find out what's there. So I just figured that's just incredibly easy for like one number typo can go unnoticed and you've done the complete opposite of what you're trying to do. I thought it was a fairly shonky language here because you're enforcing risky programming practice and bad practice too. And it turns out these asterisks are actually spaces, or you probably want that actually to be a comma because you really want to sort of use a normal thing that you'd separate concepts with. So that's, reminded me of this quote that I found somewhere on the internet, which is essentially consistency. Yeah, so I started digging through this Word document. Seriously, I found like the first thing had about 20 pages of this sort of stuff. It was just masses of repeated code. The only real differences was I could actually see a couple of these names sort of change to like temp 2, temp 3, up to sort of like temp 24 or something, and then it would repeat. So I was thinking, what the hell's going on here? Why didn't you use some loops? It turns out the language didn't actually contain loops. You were supposed to write some VB or C++ code and then call the macros with that. So instead of just mucking around with one language, you've got to go and learn to program in VB or something else. And your workflow would have to be written in some other language. So it's just putting it beyond the scientists that are not coders. The 20-page sort of this kind of thing here, that covered essentially the first error correction step of the of this process. So that was probably about 5% of the work. And I found a bunch of other Word documents. I just didn't want to look at that. So it's kind of a clear case of tools enforcing bad practice. So some other, discovered other fun things. The main thing was basically there was some horrible memory management. It turned out every line of code in that would write a result to a file. So that previous set of error corrections, that's like 11 steps. That actually wrote 11 output files. So I don't know how time-consuming that was on a desktop. And it turns out I think the researcher, because she couldn't fit like all these half a gigabyte RAM, layers into RAM at once, she basically had to sort of slice Australia up and then kind of like run these through in segments. So she's having to do all this manual work and then stitch it all back together at the end. So sort of after getting this, oh God, my brain really hurts just from seeing how she did this. And I'm also impressed that someone was actually able to like just do such boring work over and over. And it's sort of, I was just seeing there's this real technical barrier there. You've got this like massive kludge to get around using this horrible tool, but that's all the scientist had. So I sort of felt like she was trying to like shift this 1 ton of dirt with a little plastic cup. It also got worse because you've obviously got that new data is coming in regularly. So it turned out the researcher didn't like having to sort of like try and do 2 or 3 layers at once. So she ended up having to sort of let like 2 or 3 years of the data accumulate, sort of then go and like mock up some more of this code and then actually go forth and like grind through and then sort of like basically just manually stick these other layers on the end of what she'd already had. And so I've got this explanation now for why it took a really long time to get this massive turnaround of data. And it also explains why, this data, it just took years to produce. It also gets even worse. She was actually doing research in the meantime, and there was like just sort of refining some of the methods. And obviously, these can lead to sort of better results, but you can't just apply the different method to your processing halfway through because you're going to get, say, one half of your data done with one method and the other half would be done with something else. And that may have actually happened, I'm not sure. So it basically meant in 2011, she had to go back and redo the entire thing with this new method. So she's basically just duplicated all the labor again, duplicated probably some of the code. You've now got 2 versions of data, and there's probably like 2 versions of code floating around somewhere. You've got this other problem. You can't actually test that macro code. It's like, how many bugs are going to be floating around in that? and I was actually also realizing if you sort of stuff up some of the earlier steps, those results, because they're involved in the like calculation of derivative layers, you're going to end up with those sort of like bugs promulgating through all the way to your end products. You've also got all these manual steps, like constantly probably pointing and clicking through things and trying to get that workflow done manually. So there's, who knows what typos could have been introduced there, and you can't actually test that either. And also, I had no idea of what actual testing methods we used at the end to actually sort of validate these data products and whether or not they're okay. And as I've sort of seen in other areas of science, people have just sort of looked at the data that they get in the end and says, oh, okay, yep, that looks all right, so we'll keep going with it. So it really raises that question, how confident are we in that data? Pretty much boiled down to, it was a total write-off. I decided I couldn't use, there was no software I could use and I didn't want to trust that data. So I basically started over completely from scratch. So basically, given the amount of data, I thought this is probably more of a C++ problem. I'd previously used Python for a bit of terrain analysis work, and the particular algorithms I was using, it turned out to be quite slow. So I just sort of started off with GDAL, used gtest for unit testing, and I pretty much just had two sources of requirements documents. That was the Word document saying, here's some algorithms, and then a couple of academic papers which perhaps expanded on a few of the things in a bit more detail. But this was all sort of missing finer details that I didn't sort of understand, so I had to sort of work in this exploratory kind of rapid application development approach and kind of like find some details as I was going on. I immediately sort of was encountering problems because there was like certain uncertainties with this stuff. There was like I was having to sort of decide on data types up front, and some of the people that I was working with didn't actually know some of the finer details. So I was also messing with memory management and all the other fun with C, like templates. And also testing involved having to sort of like compile your tests and sort of go through this much slower cycle. So after implementing like one step, I kind of decided this is going to take a bit too long. So I went back to reconsidering Python, which is also good for lazy people like myself. I actually did a bit of evaluation up front and sort of was testing some numerical Python operations, and that actually gave me some confidence that I can actually do this in Python with GDAL, and I figured I can always rewrite bottlenecks if needed. It actually turns out that Python was one of those really good languages for exploratory development. Some of the problems just vanished with things like dynamic typing. I could sort of ignore some of the problems and just sort of concentrate on getting actual algorithms correct. Even just using the basic unit test module and nose test, that was like a much faster like turnaround of tests and things like that. And just having things like the simpler language and like simplifying other things kind of reduced that cognitive load, so I could actually concentrate more on like what is the problem I'm trying to solve, not what's this stupid memory problem or segfault that I'm getting with C++. I actually sort of was finding unit testing came in quite handy too, because that was actually enabled me to sort of like find gaps where the published models didn't actually address all your possible inputs, like sort of like how do you handle different types of no data values if you're trying to do a moving window over, say, like 9 segments of a time series, and you've got sort of mixed no data in with that. So really over this time, we're sort of able to use the unit tests to sort of like refine these algorithms down and sort of like handle no data better and add in sort of more filtering. Some of these things possibly didn't even make it into Addressee. So by the time mid-2012 came around, I had an extraordinarily rough version 1 going. It had a sort of fairly rudimentary workflow sitting over the top. I was actually able to sort of process through 12 years of data. It took about sort of 2 days at work and sort of like setting off like 2 jobs on a supercomputer, and there was a number of just constraints that I had from the code and just the environment that I was working in. But in the end, the performance of it actually wasn't too bad, and it was probably it was better than I expected. And that was even from unprofiled code. Like I didn't actually get a chance to go through and sort of find if there was really inefficient areas. So obviously, that just even this like a half-complete product reduced the manual load incredibly. So obviously, there was no way I was going to get that far with C++. So here was I decided once because I had some data, I could actually just do a rudimentary comparison of the some of the plots, and I don't know how visible it is here, but actually you can see the red plot here is the original data, and that's actually, instead of actually being a smooth distribution, there's some kind of like, it's probably some of the people up the front can probably see it's kind of jagged, so something's obviously gone wrong with that. And that's kind of gave me some evidence that there was something had gone wrong with the original production. So for a while, I was actually pulled off onto other projects, but it wasn't. Yeah, it was basically late last year I got back onto it, and I actually was able to find there was bugs in my own code, which is obviously not surprising. I was able to fix that and a couple of other sort of minor classification problems. I actually got a chance to refactor the whole thing and get rid of some of the grotty code that appeared last time. There's probably a number of temporal, sort of clearing up temporal or handling of temporal differences got stuck in as well. So I was able to like handle things like tidal zones, where obviously like if you've got a satellite flying over different times, the water will be sort of at different points, and you can. That was probably just ignored in the previous version. Yeah, so and also I was able to like completely rewrite a workflow. So it basically I was able to add in multi-processing and get some like parallel processing happening, and it also got rid of pretty much all of the manual tasks. Unfortunately, yeah, I tried to run this thing before PyCon, but then something fell over, so it's rather ironic. And sort of, yeah, working towards a summary, obviously was like, just having dealt with the project over this sort of period of time, I've got a bit blasé about it, but and it was sort of easy just to go, oh, hang on, how do I write a talk on this thing? It just seems like I've just saved someone about 20 years of their life of stuffing around with this Addressee product. But yeah, actually, sort of afterwards, sort of thinking about it in a bit more detail, realised I've actually improved some of the scientific method using Python, and well, sort of, I guess, yeah, we're really sort of like making it a more rigorous sort of body of work. So obviously, first of all, just by fixing up the horrible original workflow, it removed a number of manual steps and sources of error, so we're actually starting to like improve the rigorousness there. Obviously, using like one set of tested code to generate the data means there was just like one set of translations being applied at a time, rather than sort of that 20 pages of code before, where you've potentially got, say, different models for each step being accidentally applied because someone's done some typos. Obviously, the previous workflow wasn't documented, so that wasn't really like an open science thing. That work was kind of like stuck in the researcher's head, and you couldn't actually sort of get it out and give it to someone else. Whereas I can at least give someone this PyMODIS code and say, oh, yeah, there's the method we've used. There's also, we've actually just made a number of flexibility gains. This NDVI data is sporadically changed or updated when I think some of the underlying processing methods actually get fixed up. So in our case, we'll just be able to like set off some supercomputing jobs, rerun the thing and regenerate that data. And we don't have to go through the process of munging 40 pages of code together. And obviously there's other, CSIRO's got this group called OzCover, and they're actually about to change their underlying data format. So, but we're using GDAL, so we've got essentially a trivial fix because we can just handle the data types agnostically. Probably sort of just to throw in a few concluding points, really this project for me was like a real eye-opener as to like how difficult technology is just for some scientists. It's really like, some of them have really got such limited options, they just have to get their work done with manual labour, or they've got nothing to work with. And this isn't really the first instance of this sort of thing I've seen either. I'd also note that, yeah, I'm seeing like an increasing level of technical challenge in sort of the geospatial field as well. Like you're getting larger amounts of data, you've got sort of things like the 1 second DM of Australia is coming up. I've actually been working on that recently, and that's like a 78 gigabyte single layer. And this researcher only had about 100 gig to deal with. And obviously these sort of scaling challenges are putting it out of the reach of, or sort of working with sort of data out of the reach of many scientists. Probably another general observation is things like automated or unit testing. It's really not a tool that's understood or used by scientists. I guess I mentioned earlier that they seem to like look at data and say, okay, that seems to be plausible, or encountered instances of that. I don't really consider that, say, a rigorous testing approach. So, it's not really suited if you've got, say, complex work or perhaps like subtle things you're trying to investigate. And I would also wonder if some scientists have even got those technical skills to look at gigabytes of data anyway and actually try and verify that. I'm also sort of finding that, yeah, by introducing the testing, I was actually able to like give a much greater sort of confidence in that those results are actually matching the models that I was given. And I'd still like to actually go out and take another step, which is like model some of this data up against other independent data sets. Obviously, yeah, I'd see there's a massive need for sort of professional software development in various scientific fields. There's obviously like a lot of scope given actually the size of the data and technical challenges out there. obviously having developers would help sort of free researchers up from having to do a lot of this sort of technical stuff, and then you're actually sort of using funding more efficiently too. So instead of having someone like mucking around with 20 pages of their Addressee code, they can just go and concentrate on the methods, and someone else can spend a lot less time writing it in Python. Otherwise, yeah, I think something like the software carpentry movement, that's probably a good step in the right direction to try and like give people basic skills to avoid doing silly things. And it's like, I see this as important because geospatial data is actually sort of used in the real world. It also could be used to say like influence policy decisions at like say like federal and state level. So that you kind of there's an incentive actually to make sure that that's right. And I'd sort of, yeah, based on this, I would say I personally found Python was like a really useful general platform for actually for just getting some of this work done. It was actually far better than other tools. And it's obviously like, this is probably the first major project that I was using Python on, and it was actually changed my opinion of what it was capable of. Yeah, so much so I'm actually using it for a project with GA, which will hopefully be the subject of a talk next PyCon. Right, Q&A time.